Hello everybody, welcome back to my channel. Today we're going to be going through video 3 of my BC Calculus series. Yet again, this slideshow says day 5 because it is day 5 in the class I taught. We taught this material on day 5 in my BC Calculus class. But days 1 and 2 were just calculus prerequisites. So I will not be recording lectures for those things because they are not official calculus topics. I started recording lectures on day 3 when we got into our second unit on limits and continuity. So that is why this is video 3 and not video 5. Today we're going to be continuing through our unit on derivatives. If you're curious about the topics we'll be covering, they are outlined right here. But I don't expect you guys to know what these are just yet because we're going to be learning them today. All right, first topic of discussion is think about derivatives with our machines. Last video, let me get rid of this. Last video, we talked about the idea of a derivative as taking a function and zooming in really far, so far that it looks like a line, and then calculating the slope of this line using 2 points that are really close together. And when we do that, we take a very tiny change in our y-coordinate, dy, divided by a tiny change in our x-coordinate, dx, I apologize. So the derivative of a function at a point is just a tiny change to our y-coordinate divided by a tiny change in our x-coordinate. Because the function looks like a line if we zoom in far enough, so to find the slope, we just calculate the slope like we normally do, but make sure that the changes we're evaluating are really small. All right. And if you remember, if you're not familiar with thinking of functions as machines, it's a really useful tool to think of functions. I like to think of functions as machines that what they do is they're a machine that is programmed to do something, and it's programmed to do the same thing to everything that comes in. So the machine will take in numbers through an input port and spit out other numbers at an output port. And it is programmed to do the same thing to each number. And the thing it is doing to each number is expressed or codified with an equation. Like, for example, f of x equals x squared. This is a function I assume you're all familiar with. What this means in terms of our machines is that our machine is taking in numbers and squaring them. That's the rule it's doing. So it's coded to square numbers. So if I put in 3, I would get out 9 as my output. All right. And as a graph, we represent functions as input-output pairs. So we know that a point on the xy plane can be expressed by how far it is to the right and how far it is up. So for example, this could be 4, 4 units to the right and 4 units up. All right. So a graph of a function, all it is every single input-output pair. So if we had f of x equals x squared, we represent that as a graph by doing labeling and filling in all the points that are input-output pairs. So that would be like 3, 9 as an input-output pair because 3 is the input and 9 is the output. 4, 16 is an input-output pair, etc. So all a graphical representation of a function is every single input-output pair written as a coordinate, and you just look at the graph that creates. And when you do that and you plot every single point that's an input-output pair of this function in that order, where your x-coordinate is your input and your y-coordinate is your output, you'll end up getting the graph of the function. So that's how our machine definition of functions corresponds to our graphical representation of functions. All right. And remember, actually, I'll backtrack just 1 second. Notice how the height of our graph is the output of our function, right? If I drew y equals x squared, all right, if we look at the height at x equals 3, because the graph is just all the input-output pairs of the function, that means that this point will be 3, 9, because we know 3's output pair is 9. And what that means is that at an x-coordinate of 3, we have a height of 9. So the height of our graph is just the output of our function, and the horizontal distance of our graph is just the input. So when we calculate derivatives, remember, we take a change in our y-coordinate and divide it by a change in our x-coordinate. So if we correspond that to what we just said about our machines, that means when we calculate the derivative, we're taking a tiny change to the output of our function and dividing it by a tiny change to our input. So if I go back to the machines, what we're doing is we want to find the derivative of a function at a certain input x. We evaluate the same input-output pair, not the same input-output pair, but rather an input-output pair that is really close to this number. So we imagine that if we put in x to our function f of x equals x squared, we get out x squared. And what we do is we evaluate an input-output pair that is really close to it, like x plus 0.00001. So then its output pair would be x plus 0.00001 squared. And to calculate the derivative, we find the difference in our output and divide it by the difference in our input. And that's the same thing we did on the graph, because our outputs are the y-coordinates and our inputs are the x-coordinates. So the difference in our y-coordinates is the rise, and the difference in our x-coordinates is the run. So that's why the slope definition of a derivative corresponds to the function definition of a derivative. We are taking a change in our output and dividing it by a change in our input. So I yet again want to reiterate that you could also just think of derivatives as a change in our output to the function divided by a change to our input. And that slope that we get, or that number we get, will be different depending on what input we're looking at. Obviously, you can see that the slope of the function x squared is different depending on what x-coordinate we're looking at. Steeper up here and shallower down here. So that's derivatives with our machines. All right, differentiability. We just have to go through some. Terminology here. It's going to be boring, but we got to make sure that we understand these terms. If we can find the rate of change of a function at a point, we say the function is differentiable at that point. Differentiating a function is the same thing as finding its derivative. So if we can differentiate a function at that point, it's differentiable at that point for that logic. So yet again, if we can take the derivative of a function or find the rate of change of a function at a point, remember rate of change, derivative, slope, they mean the same thing. We say the function is differentiable at that point. It's able to be differentiated. A differentiable function, similar to our definition with continuous functions, is a function that is differentiable at every point in its domain. So if you can differentiate the function at every single point within its domain, it's a differentiable function. And a function is differentiable on an interval if it is differentiable at every point on that interval. For example, if I asked us, is the function x squared differentiable on the interval 1, 2, so from 1 to 2, you would say yes, because you can find the slope of f of x equals x squared. There's a defined slope at every point between x equals 1 and x equals 2. You can see that at each point there is definitely a defined steepness. So we would say f of x is differentiable, which I'll write diff, at, not at, I apologize. We say on this interval, 1, 2. All right, so that's some terminology. All right. So there's different ways to write a function's derivative, and I'll explain why we use different ways to express a function's derivative. All right. So yet again, all a derivative is the slope of a function at a certain point. Remember, when we calculated the derivatives in our first example, right, we took a tiny change in our y-coordinate, which we labeled dy, and divided it by a tiny change in our x-coordinate, which we labeled it dx. All right. And the slope we got would tell us the slope of the function at that point, because if we zoom in far enough, the function is a line. So taking a tiny change in y divided by a tiny change in x will give me the derivative at that point. As a result, sometimes we label the derivative as dy over dx. So that's one way to express the derivative of a function at a certain point. Or just the derivative in general. We could say, if we're trying to express the derivative of x squared, we could say that it's equal to 2x. I don't know if I covered this in the last video, but no, I think I did cover this in the last video. So I think you guys would be familiar with this. I can say that the dy over dx is 2x for x squared, because the ratio between dy over dx is going to be 2 times whatever our x-coordinate is. And we proved that last time by calculating the derivative of x squared. It just means if you take this ratio at some point x, the slope is going to be 2 times whatever our x-coordinate is. So sometimes we express the derivative as dy over dx. Remember, sometimes we express y as f of x, because remember, with our function notation, the output to our function is the y-coordinate. So sometimes instead of writing y equals x squared, we'd write f of x equals x squared to illustrate that all our y-coordinate is the function applied to our x-coordinate. It solely depends on what our x-coordinate is. So as a result, because y and f of x mean the same thing, sometimes we write our derivative as df over dx. Additionally, if you'll remember from last time, sometimes we express our derivative as f prime of x. So for example, if we were looking at the function f of x, let's say it's x squared, then f prime of x will be the function that tells us its derivative. So the f prime of x in this case would be 2x. All right, so that's another way we express a function's derivative. The derivative of f of x is f prime of x. And because y equals f of x, sometimes we denote this derivative as y prime. All right. And the last way we express derivatives is with this notation. All right. We write a d dx over here. It's kind of slanted. I don't know why I made it so slanted. D dx f of x. All right. And the reason we write it like this is you can imagine that if we were like multiply these things together, it would look like df of x over dx. And what is this? It's a tiny change in our output divided by a tiny change in our input, which with our machines, we said by definition is the derivative of a function. So you can imagine if you multiply these things together, you'd get this, which represents what a derivative is. Now, that being said, you are not multiplying d dx by f of x. This is simply a notational thing. You can think of it, here, let me backtrack. I know that sounds confusing. When you write it like this, you're not multiplying d dx by f of x. The only reason we write it like this is because it looks like if you were to multiply f of x by d over dx, you would get this form, which looks like the derivative. So that's why we write it like this. But in reality, you're not multiplying d over dx by f of x. In reality, what this notation is emphasizing is that differentiation is an operation that we do to a function, right? When we take the derivative of a function, we're doing something to the function to get a new function, all right, that expresses the function's slope at every given x coordinate. So I like this notation because it emphasizes that differentiation, or finding the derivative of a function, is an operation we do to that function. We do something to that function to find the derivative. So don't think of this as d over dx times f of x. Think of it as d dx of f of x, the derivative of f of x. It's the same kind of thing as saying, well, we know f of x is not f times x, but rather f of x just means the function at x. This does not mean multiplication. It's the same thing here. D over dx of f of x does not mean that you're multiplying the two things. It's an operation performed on f of x, but it's written this way because if you were to multiply them together, you would get a form that looks legitimate, like you get a form that perfectly encapsulates the derivative. So it's a notational thing, but in reality, this does not mean we multiply the two things together. It just means we differentiate f of x. We perform an operation onto f of x. So I apologize if that's confusing, but if all of that is confusing, all you have to remember is that this is a notation that emphasizes that differentiation is an operation you do on a function. This means you're taking the derivative of f of x. D over dx means the derivative of, and whatever you have next to it is the thing you're taking the derivative of. All right. So that is that. Here's the textbook if you want to pause and see what the textbook has to say. All right. One-sided derivatives. All right, let's do that. All right. I will say, secretly, all of the derivatives we've been calculating so far have been two-sided derivatives because of the limits we've been using. Remember when we calculated the derivative of x squared, we used this limit. We used the limit as h approaches 0 of x plus h squared minus x squared over h, right? When we calculated the derivative of x squared, we used this limit. But notice what kind of limit this is. This is a two-sided limit, all right? So what we're really doing is evaluating what this approaches as h goes to 0 from either side. And the reason that this gives the same slope is actually pretty trivial, because you can imagine that, well, as we zoom in far enough into our function, it's going to look like a line. And if I pick 2 points that are close together, it doesn't matter if the point I'm picking, let's say I want to find the slope at this point, it doesn't matter if the point I'm picking is slightly to the right or slightly to the left, because calculating the slope between these 2 points will give you the same slope because it's a line. It doesn't matter what point you choose. So that way, what it's saying is that your h value, which is the difference in your x coordinates, could be either positive or negative, and you'd still get the same slope. So if we evaluate what this ratio is, what the slope is, using 2 different points, one where h is positive, getting closer and closer to 0 from the right, and one where h is negative, getting closer and closer to 0 from the left, they'll produce the same slope. So that's why the double-sided limit works here, and we use it when we're calculating derivatives. The only issue is sometimes we can't use two-sided limits. For example, I think you'd agree with me that the function at this point, let's say I'm defining a function that looks like this, but it has 2 endpoints. The function at this point has a certain steepness at this point. I think you'd agree it's pretty flat here. But the issue is we could not take the two-sided derivative because there's nothing to the right side of this function. So even though it has a slope here, there's nothing to the right side of the function, so the two-sided limit doesn't work. The function only exists to the left of it. And as a result, we have to evaluate h values that are negative. We have to take a point to the left of of our point to evaluate the derivative because there's no points to the right of it. So we can't take a point to our right, so we can only take a point to our left. So that means that when we calculate our limit, we are only using the left-hand limit. What happens is h approaches 0 from the left. So as our distance between the 2 points gets closer and closer to 0 from the left, you're taking 2 points that are close together like this, and you're calculating the slope, and that's a perfectly valid way to do that. Yet again, we can't use the double-sided limit because there's no points to the right of it, so we can't pick a point really close to it on the right and calculate the slope because no such point exists. Same thing over here. On this scenario, there's no points to the left of it, so we'd have to use the right-hand limit. We'd have to pick a point close to it from the right because there's no point close to it on the left. No matter how close you get, there's no point to it on the left. So we can only calculate a right-hand limit because there's no point that exists on the left. So we have to calculate the slope using only points that exist on the right as they get closer and closer to each other. So that's one-sided derivatives. This slide here also goes on to explain why the derivatives we've been tackling so far have been two-sided derivatives. It says secretly all the derivatives we have calculated so far have been two-sided derivatives, which is what I said before. And it's because it doesn't matter if h is negative or positive. If the point is to the left or the right, we'll still get the same slope. And I'll just read the slide very quickly. If you'll notice, when we use limits to calculate a derivative, we use a two-sided limit. This means we're secretly finding the slope as h went from 0 to the right and from the left. This is what I said earlier. A simple diagram shows why these two are the same, hence we get a legit number for the derivative. That's what I explained just then in the Jamboard. However, at the endpoints of functions, it isn't possible for our h to extend in both directions because in one direction, the function doesn't exist anymore. So we can't take points from one side if we're at an endpoint of the function. As a result, we simply calculate the derivative using a one-sided limit like I explained. So let's go over the criteria for when a derivative will not exist, because right now we've been talking about all the cases when derivatives will exist. We've been talking about differentiability and all that stuff. But if our definitions on differentiability that we just covered, that like, for example, a function is differentiable if it's differentiable at every point in its domain, it only makes sense if we ask, well, then when is a function not differentiable? When can you not differentiate a function at that point? Because if we didn't know the answers to that question, then we wouldn't know how to define differentiable functions, because we'd be like, well, if we don't know when the derivative won't exist, then how do we know when it will exist? We have to have some criteria, otherwise our definitions for differentiable functions, differentiable intervals, stuff like that, they don't make sense. Because how are we supposed to know whether a function is differentiable at every point if we don't know the criteria for when it will be differentiable or not? So that's why this is important. So quite obviously, our derivative will not exist if our limit that calculates derivatives doesn't exist. If our limit definition of derivative does not give us a number, then our derivative won't exist because that limit tells us our derivative. If the function is not locally linear at that point, it additionally will not be differentiable at that point. Because remember, our whole definition of derivatives relied on the fact that as we zoom in really, really far to a function, it looks like a line. If that doesn't happen, if you zoom in far enough and it doesn't look like a line, we can't calculate the slope of the rate of change at that point, because our whole definition is contingent on the fact that functions are locally linear and you can take the slope of lines. All right. So if we zoom in and it doesn't look like a line, our whole definition breaks down. We can't calculate the derivative anymore. If the point has two slopes, depending on what side you look at, that would mean the left hand and right hand derivatives are different, and the two-sided derivative doesn't exist. I'll show an example of this with the absolute value function. Our absolute value function looks like a v. As you'll notice, if I have I'll go to Desmos and try and illustrate this. All right. So if I ask you to find the derivative of this function at x equals 0, you could do one of two things. You could notice, well, as I zoom in, no matter how far I zoom in, it doesn't look like a line. It still looks like a v. So it's not locally linear. Therefore, I can't differentiate it. Or you could realize, well, in order for a function to be differentiable, it has to have a two-sided limit, because our original definition of derivatives used two-sided limits. And if we evaluate a point really close to x equals 0 from the left and calculate the slope, we're going to get -1. If we evaluate a point really close to x equals 0 on the right and calculate the slope, we're going to get x equals +1. So clearly, the two-sided limit doesn't exist because the one-sided limits, for example, if we were to calculate our limit as h goes to 0 from the left, which means we're calculating a point really, really close to x equals 0 from the left, we get a slope of -1. But if we did it as h approaches 0 from the right, we get a point really close to x equals 0 from the right, which would give us a slope of 1. So the two-sided limits do not produce the same slope, or sorry, the two one-sided limits do not produce the same answer, and hence the two-sided limit does not exist. Therefore, if our two-sided limit defines what a derivative is at that point, at any point that is not an endpoint, remember we used one-sided derivatives to find the derivatives at endpoints. Notice how this is not an endpoint of the function. It's perfectly defined here, and it's in the middle of the function. So it's not an endpoint, and then we would have to use our original definition of derivatives where we calculate the two-sided limit, but that limit doesn't exist, and hence so that means that the function is not differentiable at this point. That's just a long way of saying that the function will not be differentiable if the limit doesn't exist, if the two-sided limit doesn't exist, which can occur if the two one-sided limits are different from each other. All right. If there's a discontinuity at that point, the function will not be differentiable. We'll get to that in a second. If the slope is vertical, if the slope is vertical, the slope is undefined, so the derivative won't exist. For example, if we look at the graph of the function, the cube root of x, notice how the function is vertical at x equals 0, so the derivative will be undefined here because an undefined slope, a vertical slope is an undefined slope. So if we take the derivative at x equals 0, we will not get an answer. The function is not differentiable at x equals 0. All right. Ultimately, like I said, differentiable functions must be locally linear because if our whole definition of derivatives are contingent on the fact that functions look like lines as we zoom in and we can calculate the slope of lines, then if a function is not locally linear and we can't zoom in far enough to make it look like a line, then our whole method for calculating derivatives doesn't work anymore, hence it won't be differentiable. So differentiable functions must be locally linear for that reason. All right, differentiability implies continuity. The theorem is as follows. If a function is differentiable at a point, it is also continuous at that point. And we're going to prove that very quickly just by looking at each continuity type individually. All right, so yesterday we defined two types of point discontinuities. One type of point discontinuity is when the function is perfectly valid until you get to a certain point, let's say it's x equals 2, and the value that you think the function would be at that point is not the value, but rather the value of the function at that point is some other value that seems kind of weird. All right. If we have this kind of discontinuity, notice what happens if we try and calculate the slope at x equals 2. All right. So by our limit definition of a derivative, if we want to find the derivative of this function at x equals 2, all right, we'd take the limit as x approaches 0 of f of x plus h minus f of x over h. All right. And what that means is we're taking a point really close to x equals 2 and calculating the slope between those 2 points. All right. So we can do that from either side. And notice that as our points get really, really close to this hole, all right, the slope in between where our function is defined and the point really, really close to it gets steeper and steeper and steeper. So the limit doesn't approach a real number, but rather as our points get closer and closer and closer to this hole, the slope will become vertical, right? So that means that the limit does not produce a real number, and therefore our slope is undefined. It doesn't exist at this point, and therefore we cannot differentiate the function at x equals 2. The next type of point discontinuity is a lot easier to show why you can't differentiate it there. In order for us to be able to differentiate a function at that point, notice how this definition says we have to be able to find the value of the function at that point. If this is undefined, then our limit's going to be undefined, because if this is undefined, we're going to get not a number for our limit, and it just won't be a real answer. So if our function is not defined at a point, then our limit won't exist and our derivative won't exist. Here, if there's a hole and the function is not defined here, then f of x doesn't exist, and therefore it is not differentiable by our limit. So to recap, the reason this is not differentiable is because if you pick a point, actually, let me reiterate. If you have a function that that approaches some value from either side, but the function is not what it would look like it would be at that point, but rather some other value, if you try and calculate the slope using this point and then 2 points really close to it, or 2 points that have an x-coordinate really close to it, your slope is going to basically become infinite. And we know that if our slope is infinite, then our limit isn't a real number, and therefore the derivative doesn't exist. Additionally, you can also remember from our vertical tangent, an infinite slope means a vertical line, which is an undefined line. So the function is not differentiable. And here, the function is not differentiable simply because it's not defined it's not defined at our x coordinate. F of x does not exist. And in order for our derivative to exist, we have to know what the value of f of x is. So if it doesn't exist, then our derivative doesn't exist. All right. The next example is a jump discontinuity. If we have a jump discontinuity, the same thing occurs. If we try and calculate the derivative at this point, you'll notice that the two-sided derivatives are different. If you calculate the derivative if you calculate the right-hand derivative, the derivative as x approaches 0 from the right, you'll notice that the slope is 0. The slope between these 2 points is 0. But if you calculate the derivative of this function using a one-sided derivative as x approaches 0 from the left, you'll end up getting a point down here because you're basically looking at points that have an x coordinate that are just barely to the left of this one. You'll get points over here, right? And you'll notice that the slope of these lines, the line between these 2 points, approaches infinity. So not only is this an undefined slope, but the one-sided and two-sided limits are not equal to each other, and therefore the limit as a whole does not exist. So that's why a jump discontinuity will mean that the function is not differentiable at that point of discontinuity. Additionally, infinite discontinuities are easy as well. If we have an infinite discontinuity, right? Remember, if a function goes up and up to infinity around a point, that means we have a vertical asymptote there. And it also means that the function is not defined at that point. Let's say this is x equals a, all right? That means that f of a does not exist, right? And in order for us to be able to take the derivative of a function at an x coordinate, we have to know what the value of the function is there. Because remember, we're taking f of x plus h minus f of x over h. If we don't know what f of x is, well, then we can't find the limit. So this is why infinite discontinuities don't work. The last kind of discontinuity is an oscillating discontinuity, and it's pretty simple using Desmos to show why this kind of discontinuity will make the function not differentiable. So for example, we know that this function is not continuous at x equals 0 because it doesn't approach anything from last video. But if I asked you to tell me what the slope was, or what the slope is at x equals 0, or as we approach x equals 0, well, first of all, we could say two things. Well, we know that at x equals 0, the function is undefined because 1 over 0 is undefined. So with that, what we said in all our other examples that if the function is undefined at the point we're looking at, then the derivative won't exist. But also, the slope doesn't approach anything either. The slope from either side goes up, and then it goes down. So it's really large, and then it's really small, and then it's really large, and it's really negative, stuff like that. So the slope doesn't approach anything either. So not only is the function not defined at x equals 0, but the slope also doesn't approach anything either. It just goes up and down and up and down and up and down. It goes to negative infinity, positive infinity, etc. It's just a whole mess. So that's why oscillating discontinuities are, if you have a point that is has an oscillating discontinuity, it will not be differentiable there. So there you have it. We just went through every single kind of discontinuity and showed how at every single point in discontinuity, you cannot take the derivative at that point. That means if you can take the derivative of a function at that point, then the function must be continuous there. Because we showed that if it's discontinuous, you can't differentiate it. So if it is continuous, so if it is differentiable, that means it has to be continuous. So that's why differentiability implies continuity. Note that the opposite is not always true. And the key example is with the function we were using earlier, the absolute value of x. Notice how the function is continuous at x equals 0, right? You can draw through it with one pencil stroke, but it's not differentiable there. We explained why it's not differentiable here. So continuity does not imply differentiability. You can't say the opposite is true, but you can say differentiability implies continuity. If a function is differentiable, it's continuous there. So that's differentiability implies continuity. All right. The intermediate value for f prime of x is a very simple theorem. It's similar to the theorem that we outlined yesterday, which is also pretty simple. It basically says if a function is differentiable on a certain interval, all right, and that means that it's continuous because if a function is differentiable, it has to be continuous, like we just outlined, and it doesn't have any sharp corners or vertical tangents, right? So remember, the function won't be differentiable if we have like we call this a corner where the slope is different on either side, or a vertical tangent, or it's not locally linear. So the function cannot have corners. It cannot have vertical tangents. It has to look kind of like this. We call it a smooth curve. All right. The function, the theorem says that if we take the derivative at the first point in our interval, which would be f prime of A. Let's say this is x coordinate A, and this is x coordinate B. All right, and we took the derivative of our function at the other endpoint, which would be f prime of B. This says that the slope of the function, the derivative, will take on every single value between f prime of A and f prime of B. What does that mean? Well, it means that if you have some number, let's say y naught, that is in between f prime of A and f prime of B, or equal to f prime of A or f prime of B, it says that at some point in this interval, the slope will be equal to whatever number you want in between these two numbers. And you can see why that's true. Notice how the slope doesn't jump at all. The slope changes continuously. For example, the slope here is negative, and it gets closer and closer to being 0, and then it gets gradually more and more positive. The slope never jumps up to a certain value. It changes gradually, right? So basically the slope, if it wants to get from this slope to this slope, it has to cover every single steepness in between, because it doesn't jump. There's no corner. It doesn't jump rapidly. It changes its slope gradually. So if it wants to get from this steepness to this steepness, it has to cover every single steepness in between. That's what this is saying. If you have two endpoints of a function and you take their slope, any steepness or any slope in between those two slopes that you found will be the derivative of the function at some point within the interval, because the function has to change gradually if it's differentiable. So therefore, the derivative will take on every single value in between whatever the slope is at x equals A and whatever the slope is at x equals B. I hope that makes sense. And here's the definition written in more formal language if you are curious. But it's the same thing that I said. All right, this is for tomorrow. Come back for tomorrow to learn these rules. And the last topic of the day is the idea of second and higher order derivatives. Sometimes when we find the derivative of a function, we get a function that we could take the derivative of again. If we were to do this, the second derivative we would get would be called, go figure, the second derivative of the original function. For example, we learned yesterday that the derivative of x squared is 2x. And if I ask you what the derivative of 2x is, it says it's asking you to tell me what the slope is of the function 2x at an x coordinate x. And you notice that, well, the slope of 2x is the same everywhere. It's always 2. So the derivative of 2x is 2, because the function 2 tells us what the slope of the function is at every x coordinate. And it doesn't depend on what the x coordinate is, because you'll notice that the slope is the same everywhere on the line y equals 2x. So if we took the derivative of 2x, it's asking what's the rate of change of 2x at every point, and it's just 2. It's always 2. The rate of change is always 2 on 2x. All right, so the derivative of 2x is 2. And you'll notice that we got 2 by taking the derivative of 2x, which is the derivative of x squared. So 2 is the second derivative of x squared, because when you differentiate x squared, you get 2x, and you differentiate it again, you get 2. You differentiated it twice. 2 is the second derivative. Additionally, if you were to take the derivative of 2, you would get 0. That's because the line y equals 2 looks like this. It looks like a flat line, and it has a slope of 0 everywhere. So if you differentiate 2, you're going to get 0, and then therefore 0 would be the third derivative. I don't know why it's doing that. Derivative of x squared. All right, so that's the idea of higher order derivatives. When I say the third, second, fourth derivative of a certain function, it just means you differentiate that function, then differentiate that function, etc. However many times it's telling you to do. So second derivative means you differentiate x squared, then differentiate that. The third derivative means you differentiate x squared, then differentiate that, and then differentiate that, etc. So that's what higher order derivatives are. If you see like fifth order derivative, you know that it means to differentiate the function, then differentiate the one you get, then differentiate the one you get, etc. 5 times. That's what it means. Additionally, the first derivative is just the derivative of the function. Go figure, because you're only differentiating once. So the nth derivative of a function just means you take a function and you differentiate it n times. So you differentiate x squared, and you'll get 2x, and then you differentiate 2x, and you'll get 2, etc. And you do that pattern however many times it's telling you to do. So if it's the fourth derivative, you do the differentiation process 4 times. We'll get into why higher order derivatives are a useful tool, but all I need you guys comfortable with right now is what they are. and the idea of how you would find them. If you knew how to calculate the derivatives of the intermediary functions, I want you comfortable with the idea that if I wanted to find the second derivative of a function, I would just differentiate it and then differentiate its derivative, etc. So I just need you guys comfortable with the idea of what higher order derivatives are and the process of finding them, even if you couldn't find them on your own just yet. All right, let's go back to the slideshow. And the slideshow is saying what I said. But the last thing we have to cover is how to denote higher order derivatives, and it's actually pretty simple and pretty easy are pretty simple and pretty similar to how we define derivatives. So remember how we defined the first derivative of a function as f prime of x, or the derivative of a function as f prime of x. So if you take the derivative of this, you can think of it as f prime of x, so f double prime of x, if that makes sense. So we could say the nth derivative is just f with n apostrophes. So this would be the fourth derivative of f of x. You have 4 apostrophes. Additionally, because remember we said that we could write the first derivative as y prime, we could write the second derivative as y double prime, third is y triple prime, etc. So however many apostrophes you have is however many derivatives you've taken of your function y. Additionally, we sometimes express higher order derivatives as, for example, the second derivative would be expressed as d squared y over dx squared. The third derivative would be d cubed y over dx cubed. And the pattern continues. The nth derivative would just be d to the ny divided, over dx to the n. That's the nth derivative. You see how this is the second derivative, this is the third derivative. So if we're taking the nth derivative, like the fourth derivative, it would be d to the fourth y divided by dx to the fourth. That's the pattern. Additionally, I could write using this notation. If I want to find the derivative of a function, if I want to find the higher order derivatives, I would just write whatever order derivative I'm taking like this, d squared over dx squared. So this means I'm calculating the second derivative of f of x. This means I'm calculating the third derivative of f of x. And this means I'm calculating the nth derivative of f of x. So that's different ways we express higher order derivatives of functions. So if you see these in a textbook, that's what it means. This means we're finding the second derivative of f of x. And what I'll do is I'll actually go into Symbol Lab and show you how that works. Because remember we said that the second derivative of x squared, because when we differentiate 2x, we get 2, is 2. So if I plug that in, I said I want to find d squared over dx squared, not that, d squared over dx squared of x squared. I want to find the second derivative of x squared in the notation that we just that I just taught you guys. If I plug it into Symbol Lab, we will indeed get an answer of 2. So I hope you can see that I can't really BS it. This is a computer telling you that this is true. This is how we write second derivatives. We write it like this. And when we take the second derivative of x squared, we get 2 like we would expect, because when we did it on our own, we also got 2 as our answer. All right. Let's go back to the slideshow. All right. So I don't know what it's saying down here, but oh, okay. Let me read this. So the top ones were saying what I said. I apologize. We could denote the second derivative of a function as y double prime or d squared y over dx squared. That's the way I was explaining earlier. Additionally, we could express the third derivative as y triple prime or d squared y over dx cubed. We could also express it as f triple prime of x. All the ways that I just explained. And the bottom thing is just saying that if you want to find the next derivative of a function, you just take the derivative of the previous function. That's what it means. So the nth derivative of a function is the derivative of the n minus 1th derivative of our function. And we see how this works with x squared. The second derivative is the first derivative of x squared, which is 2x, and you take the derivative of it. That's what this is saying. All right, so that's it for today. I hope that made sense. I hope you guys learned something today. As always, please leave any questions in the comments, and I will answer as many as I can. stay tuned for the next video where we're going to keep working through derivatives and learn some derivative rules. And I hope to see you there. Have a good day, and thanks for watching.